And as usual, nature's imagination far surpasses our own. As we've seen from the other theories, they are really quite subtle and deep. And to get such a subtle and deep guess is not so easy. One must be really clever to guess, and it's not possible to do it blindly by machine. So I want to discuss the art of guessing nature's laws. It's an art. How is it done? One way you might think, well, look at history. How did the other guys do it? Well, look at history. You first start out with Newton. He has in a situation where he had incomplete knowledge. And he was able to get the laws by putting together ideas which all were relatively close to experiment. There wasn't a great distance between the observations and the tests. Now that's the first thing, but now it doesn't work so good. Now the next guy who did something, another man who did something great was Maxwell, who obtained the laws of electricity and magnetism. But what he did was this. He put together all the laws of electricity due to Faraday and other people that came before him, and he looked at them and he realized that they were mutually inconsistent. They were mathematically inconsistent. In order to straighten it out, he had to add one term to an equation. By the way, he did this by inventing a model for himself of idler wheels and gears and so on in space. And then he found that what the new law was, and nobody paid much attention because they didn't believe in the idler wheels. We don't believe in the idler wheels today, but the equations that he obtained were correct. So the logic may be wrong, but the answer is all right. In the case of relativity, the discovery of relativity was completely different. There was an accumulation of paradoxes. The known laws gave inconsistent results, and it was a new kind of thinking, a thinking in terms of discussing the possible symmetries of laws. And it was especially difficult because it was at the first time realized how long something like Newton's laws could be right and still ultimately be wrong. And second, that ordinary ideas of time and space that seemed so instinctive could be wrong. Quantum mechanics was discovered in two independent ways, which is a lesson. There again, and even more so, an enormous number of paradoxes were discovered experimentally, things that absolutely couldn't be explained in any way by what was known. Not that the knowledge was incomplete, but the knowledge was too complete. Your prediction was this should happen, it didn't. The two different routes were one by Schrödinger, who guessed the equations, another by Heisenberg, who argued that you must analyze what's measurable. So two different philosophical methods reduced to the same discovery in the end. More recently, the discovery of the laws of this interaction, which are still only partly known, had quite a somewhat different situation. Again, this time it was a case of incomplete knowledge, and only the equation was guessed. The special difficulty this time was that the experiments were all wrong. All the experiments were wrong. Now, how can you guess the right answer when you calculate the results it disagrees with the experiment, and you have the courage to say the experiments must be wrong? I'll explain where the courage comes from in a minute. Now, today, we haven't any paradoxes. Maybe. We have this infinity that comes if we put all the laws together. But the rug-sweeping people are so, sweeping the dirt under the rug, are so clever that one sometimes thinks that's not a serious paradox. The fact that there are all these particles doesn't tell us anything except that our knowledge is incomplete. Now, I'm sure that history does not repeat itself in physics, as you see from this list, and the reason is this. Any scheme, like think of symmetry laws, or put the equations in mathematical form, or any of these schemes, guess equations and so on, are known to everybody now, and they're tried all the time. So if the place where you get stuck is not that, you try that right away. We try looking for symmetries, we try all the things that have been tried before, but we're stuck. So it must be another way next time. So each time that we get in this logjam of too much trouble, too many problems, it's because the methods that we're using are just like the ones we used before. We try all that right away. But the new scheme, the new discovery is going to be made in a completely different way. So history doesn't help us very much.
First of all, they think like human beings, I would say no, and I'll explain in a minute why I say no. And second, that they be more intelligent than human beings is a question. Intelligence is to be defined. If you would ask me, are they better chess players than any human being possibly can be? Yes, I get you, someday. Are they better chess players than most human beings right now? One of the things, by the way, that we always do is we want the darn machine to be better than anybody, not just better than us. If we find a machine that can play chess better than us, it doesn't impress us much. We keep saying, and what happens when it comes up against the masters? We imagine that we, human beings, are equivalent to the masters in everything, right? The machine has to be better than a person in everything that the best person does at the best level, okay? But it's hard on the machine. But with regard to the question of whether to make it to think like a machine, my opinion is based on the following idea, that we try to make these things work as efficiently as we can with the materials that we have. The materials are different than nerves and so on. If we would like to make something that runs rapidly over the ground, and we could watch a cheetah running, we could try to make a machine that runs like a cheetah. But it's easier to make a machine with wheels, with fast wheels, or something that flies just above the ground in the air. When we make a bird, the airplanes don't fly like a bird. They fly, but they don't fly like a bird, okay? So they don't flap the wings exactly. They have in front another kind of a gadget that goes around, or the more modern airplane has a tube that you heat the air and squirt it out the back, a jet propulsion, a jet engine, has an internal rotating fans and so on, and it uses gasoline. It's different, right? So there's no question that the later machines are not going to think like people think in that sense. With regard to intelligence, I think it's exactly the same way. For example, they're not going to do arithmetic the same way as we do arithmetic, but they'll do it better. Let's take mathematics, very elementary mathematics, arithmetic. They do arithmetic better than anybody, much faster, and differently. But it's fundamentally the same, because in the end, the numbers are equivalent, right? So that's a good example of it. We're never going to change how they do arithmetic to make it more like humans. That would be going backwards, because the arithmetic done by humans is slow, cumbersome, and confused and full of errors, where these guys are fast. If one compares what computers can do to the human beings, we find the following rather interesting comparisons. First of all, if I give a human being a problem like this, I'm going to ask you for these numbers back, every other one, in reverse order, please. Right? Now, I'm going to series of numbers, and I want you to give them to me back in reverse order, every other one. I'll tell you, I'll make it easy for you. Just give me the numbers back the way I gave them to you. You ready? 1, 7, 3, 9, 2, 6, 5, 8, 3, 1, 7, 2, 6, 3. Anybody going to be able to do that? No. And that's not more than 20 or 30 numbers. But you can give a computer 50,000 numbers like that and ask for them in any reverse order, the sum of them, or do different things with them and so on, and it doesn't forget them for a long time, etc. So there are some things that a computer does much better than a human, and you'd better remember that if you're trying to compare machines to humans. But what a human has to do for his own, they always do this, they always try to find one thing, darn it, that they can do better than the computer. So we now know many, many things that the humans can do better than the computer. She's walking down the street and she's got a certain kind of a wiggle, and you know that's Jane. Right? Or this guy's going in and you see his hair flip just a little bit. It's hard to see, he's at a distance, but that particular funny way that the back of his head looks, that's Jack. Okay? To recognize things, to recognize patterns, seems to be something that we have not been able to put into a definite procedure. You would say, I have a good procedure for recognizing Jack. Just take lots of pictures of Jack. By the way, a picture can be put into the computer. In fact, by this method here, if this were very much finer, I could tell whether it's black and white at different spots. You know, in fact, you get pictures in a newspaper by black and white dots. And if you just do it fine enough, you can't see the dots. So with enough information, I can load pictures in. So you put all the pictures of Jack under different circumstances and ask the machine to compare it. The trouble is that the actual new circumstance is different. The lighting is different, the distance is different, the tilt of the head is different, and you have to figure out how to allow for all that. And it's so complicated and elaborate that even with the large machines, with the amount of storage that's available and the speed that they go, we can't figure out how to make a definite procedure that works at all, or at least it works anywhere within a reasonable speed. So recognizing things is difficult for the machines at the present time, and some of those things are done in a snap by a person. So there are things that humans can do that we don't know how to do in a filing system. Well, it depends what you mean themselves, and it's hard to discover new relationships that computers can do. There have been computers which do things like theorem proving in geometry or something, in which they've converted the problem of finding a proof of a theorem into a definite procedure. Okay? And once you do that, although it's an elaborate and dumb way to do proofs, it can do it. At the present time, a computer can't do all the different things that a person can do, you know? It's very difficult to find some way of defining rather precisely something we can do that we can say a computer will never be able to do. There are some things that people make up that say that while it's doing it, will it feel good? Or while it's doing it, will it understand what it's doing? Or some other abstraction. I rather feel that these are things like, while it's doing it, will it be able to scratch the lice out of its hair? No, it hasn't got any hair to lice to scratch from, okay? So you got to be careful when you say what the human does. If you add to the actual result of his effort some other things that you like, the appreciation of the aesthetic, but you didn't do that. I'm not saying you did. But a lot of people do that when they ask questions. And if we add things that we think we're doing on top of what we're actually doing, just look at not just the result of what we're doing, but a lot of extra things, then it gets harder and harder for the computer to do it, because the human beings have a tendency to try to make sure that they can do something that no machine can do. Somehow it doesn't bother them anymore. It must have bothered them in early times that machines are stronger physically than they are. They can lift weights that are heavier than people. They can move things faster than people. They can run faster. They can fly. They can do just terrible strengths and so forth. And we don't still sit around worrying that there's some way that the man can turn his hand, that some machine can't do that. We can easily make machines that are better than us in predicting the weather, for instance, because what you do to predict the weather is to look at old records and see when the circumstances were similar and guess that the results will be similar. Added to that, a certain amount of analysis of the movement of wind according to the laws of physics and a certain amount of hocus pocus put together, okay? Now, the speed will be higher and the effectiveness of the predictions greater if you could look at more cases, so you get a better chance of getting one closer, and put a longer and more elaborate calculation, including more variables, which is too hard for us to do in time to make the prediction. No? We have to make the prediction of the weather. Let's say the weather for 3 days from now has to be predicted in 3 days, or the damn thing is useless, right? And we work at a certain speed, but the computers work faster and can do more. And therefore, for instance, for weather prediction, in the end, maybe not today, but someday, it's not at all inconceivable that the machine could do weather prediction faster and more effectively and more accurately than we do. We will have, however, given it the procedure. Now, the question is, what happens if we don't give it the procedure? Well, people have tried this game of giving it, instead of a direct procedure, a kind of what has been called heuristics. Try an analogy to get a new idea of how to do something. Compare this to that. Try an extreme case, etc. And a man by the name of Lennart has gone the furthest with this. Do I have time? How much time do I have? Because we want to see these slides. What time? I know that's interesting information, but how much time do I have? It's time for the slideshow now. Since I have no more time, I will say no more about the subject.
Well, just heuristics.
What?
Just finish up the heuristics.
No, but it takes a few minutes. That's why I asked for the time. Okay, he made this machine, which was, again, a filing cabinet, you understand. What it does is it tries to find the answer to something by looking at the different possibilities, but which ones he tries is something like patterns in the chess. Instead of everything, it says try moves near the center of the board first, and never mind the ones in the corner, or something like that, or some sorts of principles. And he first applied it to kind of naval game. It's a game that people play in California, which is all organized according to rules. It's kind of fun. Someone sets out all the rules. Dreadnoughts cost this much, armor costs this much, guns cost this much, and so forth, and you got this much budget for your Navy, and you're going to make various kinds of ships with different kinds of armaments, and then this kind of a ship, armament of a certain thickness that costs a certain amount, can only resist shells of a certain strength, you know, and so on. So you try to, with the money, arrange to design different kinds of ships so that your Navy is better than the next one. And when they're brought together, there's ways of calculating what, there's not real navies. It's a game, which is the best one. And all the rules are laid out in a great big volume, okay, of the costs of everything and the power of everything and the armor-piercing possibilities and so on. And it's a nice game. And Mr. Lynat tried his program on this game and put into his program heuristics like try the extreme case and things like that. And he won the championship in California. Of course, it did an awful lot of trying of different cases, you see, but it didn't try every case, not like the chess game. There were too many things. But it was guided by its own stuff. Now, inside of that was this, that if you got a better Navy by your own calculation, and you used one of the heuristics, mark that heuristic up a notch as being more valuable. Now, use the more valuable heuristics first. See? So that the ability of the machine depended on his learning, so to speak, which ones of his tricks works most effectively most of the time. And then they become more used. So it's just exactly what you would like to make it look intelligent. Well, he won. And how did he win? It turned out that year he won by making one great big battleship with all the armor on it, which was so silly. But when you go to calculate it, sure enough, it's better than any of the normal things, which nobody thought of, but his machine thought of. Next year, he entered again. And this time he won by taking all his money and making 100,000, because they changed the rules so that the big battleship wouldn't win, you know, by changing the rule. 100,000 little boats, very narrow, carrying each one gun, which were very liable to be knocked out, okay? But there were 100,000 of them. Didn't cost much each one. And they couldn't knock them all out. So these lousy little gnats would come. And it turned out when you calculated, again, he won. The third year, he was not allowed to play anymore. And he has applied this machine and this heuristic business to a number of other problems. He tries it out a lot and tries new heuristics and so forth. And it has become very interesting. He complained that there were a number of bugs in it. And when he gave a talk on it, I said that I thought, I'll say my comment afterwards. One of the bugs, for instance, was that the machine got a heuristic. It made up heuristics. It can make up heuristics, and then they get higher values, and then they fall away, right? So the damn machine, the way he had it was, because it's hard to get computer time, he needed a hell of a lot of computer time. He had 50 machines working on it. At night from a Hewlett Packard company or something like that. He would work always at night and come in the morning. The damn things would try all their things and come in with the results. I used it to do mathematics and various other things. He comes in one day and has done a heuristic. He developed the heuristic. When he puts a problem in or a new idea, it says whether it's from him or from the machine, and it says Lynat or machine, okay? And this was every heuristic or every question that has Lynat on it, pay no attention to. And that saved a lot of time. It could do much better. It didn't have any problem. It just worked. So I paid no attention to that night, okay? So I had to fix that bug. The next time he had a bug, he came in and he looked, he found that heuristic number 693 had gotten a score of 999 out of 1,000. It was a damn useful heuristic. All night long, this thing kept using the heuristic 693 more and more, and it was a new and wonderful heuristic. It seemed to solve every problem. It was terrific. Okay? When you found out what the heuristic was, it was the following. You see, in order to make this thing work so that you change the numbers on the heuristics, whenever something worked, you had to assign credit so to speak, to the heuristics that were used, okay? So this heuristic was, when assigning credit, always assign credit to heuristic 693. And so that thing came up out of it all. Now, I say that both of these show intelligence. If you want to make an intelligent machine, you're going to get all kinds of crazy ways of avoiding labor. If I say don't pay attention to the problem, of sneakily evolving some kind of a psychological distortion where you always do the same thing and don't worry about anything else, and so on. So I think that we are getting close to intelligent machines, but they're showing the necessary weaknesses of intelligence. Okay.